This is lecture 6b on the average value of functions. Recall from arithmetic that there's several averages for a list of numbers. There's the mean, the median, the mode, and when you get into algebra and statistics, there are even more averages. When it comes to functions, there are different kinds of averages as well. There's the average slope, the average value of the function, and then there's another commonly used average, the root mean square, which is a quadratic mean of the function. This is used for periodic functions. In this lecture, I'm going to discuss the average slope and the average value of the function and relate them to two theorems, the mean value theorem for differentiable functions and the mean value theorem for integrals. So if you can kind of make this association here, so the mean value theorem for differentiable functions has to do with the average slope. The mean value theorem for integrals has to do with the average value of the function itself. So I'm going to start with the mean value theorem for differentiable functions, and this has to do with getting speeding tickets. Okay, the statement of the mean value theorem here is that if f is continuous on some interval a, b, and is differentiable on the open interval a, b, then there's some value of x, which I'm calling c. So this is c. It's some value of x in this interval a, b, where the derivative is equal to the average slope of the function. This is the average slope of a function between a and b. You have to specify the endpoints here. So between a and b, you take the function at b minus the function at a divided by b minus a. That is your average slope, and I'll show you a picture of it in a minute. This theorem says there is some value of x in a, b where the derivative is equal to this average slope. So here's a graph demonstrating that theorem. Okay, so we're looking at some function in red line, and we look at it between 2 and 7. So 2 is a, and 7 up here is b. Now to find the average slope, you take the value of the function at b, which is right here, subtract the value of the function at a, over here, divide by those endpoints, which would be 7 minus 2. Whoops, 7 minus 2, because a is 2. Okay, that's your average slope. The theorem says that somewhere between 2 and 7, the derivative of the function is the same as the average slope. Here I've drawn the tangent line showing you the slope of the tangent line is equal to that average slope. Now how this applies to getting a speeding ticket, I guess this applies on certain turnpikes. It's written down. I have never gotten a speeding ticket because of this, but I understand this is true. Say on the turnpike they pick you up at 2 locations and they compute your average speed between those 2 locations. Say your average speed comes out to be 100 miles per hour. The mean value theorem for differentiable functions says that somewhere between this time and this time you were indeed going 100 miles an hour, and that's enough to warrant a speeding ticket. So now you have an application for the mean value theorem for differentiable functions. Now we're going to look at the average value of the function itself. And we're going to do the same drill that we always do in calculus. We don't know how to do a problem. We break it down into little linear pieces. We sum up over those little linear pieces. Then we refine the approximation by making a finer and finer mesh, more and more little pieces. Finally, we get to a point where we have an infinitesimally small mesh, but we have this big sum here. Okay, let me get the highlighter. So I'll have this sum, but n is getting larger and larger as we refine the mesh, and so in the end we take the limit. In other words, we take the limit as n goes to infinity and we jump over from a finite sum to a definite integral. So this is exactly what we've done all along, and that's going to be our average value for a function. And here is the end result. So this is the average value. We're defining it to be the limit as n goes to infinity of all these little averages. We're just picking a value of the function and multiplying it by the width of the mesh divided by b minus a. And if we take the limit, this Riemann sum becomes the definite integral. So we have the definite integral of the function between a and b divided by b minus a. We define that to be the average value of the function. So here's an example. Let's let our function be x squared, and we're going to look on the interval 0 to 2. So our a is going to be 0 and b is going to be 2. Here's the formula. We simply plug into that. So the function is x squared. We integrate it between 0 and 2, divided by 2 minus 0, and we get 4/3. That's the average value of the function x squared on the interval 0, 2. And this is a graph of what we just did. Here's x squared. Here's its average value. In this case, again, a was equal to 0, b was equal to 2, and we integrated from 0 to 2 x squared dx and divided by 2 minus 0, and that's the average. Turns out to be 4/3. Obviously, the average value is specific to the interval of the independent variable. An example, if you take the average value of sine between 0 and pi, you get pi over 2. If you take the average value of sine between 0 and 2 pi, the answer is 0. Now that we know the average value of the function, we can look at the mean value theorem for integrals, and you will see a parallel between this and the mean value theorem for the differentiable functions. The mean value theorem for integrals states that for the function f that's continuous on the interval ab, and we want a not equal to b, then there is some value of x, which I'm calling c, in that interval where the function equals the average value. And that's what the mean value theorem for integrals says. So here's that comparison. This is the mean value theorem for the differentiable functions. It says there is at least one point along the graph where the derivative is equal to the average slope. That's stated in words, and this is of course for a continuous function. Here is the derivative f prime at some value of c, at least one value of c. It's equal to this, which is the average slope. Now the mean value theorem for integration, or integrals, says that there is at least one point along the graph where the continuous function equals its average value. You see the statements are about identical. Okay, and this is your average value. The c is not necessarily the same. The c that's up here is not equal to the c that's down here. The average value can be very useful. If you look at the definition of this average value, here's the definition, well, from the mean value theorem, there is some c that's equal to the average value. Okay, so I'm going to write that as the average value. You can even, okay, average, fine. Now multiply both sides by b minus a, which the result is that the definite integral here from a to b is equal to the average value times b minus a. So all this says is that if the area under the rectangle created by the average value and b minus a is equal to that entire integral of the function between a and b. So here's a demonstration of that. What we're looking for here, what we're looking at here, rather, is this continuous function x squared, and now we're looking at it over ab. The interval ab is 0 to 4. Okay, the average value, here's the average value right here, and if I look at the area under this average value, so this area would be the average value times 4 minus 0, that's the area under here, that is equal to the integral from 0 to 4 of x squared dx. If you want to think of it mentally, you can think that this little piece here got chopped off and put over here, and that's why they're equal.